Okay, so we're going to go over some exercises. So you may have noticed that on Scala there is already another video. This is the same. I did the same activity more or less last year with last year's class, and we already have those exercises done together in class. And I put the recording on your Scala, so you feel free to go through those as well. Those were the ones that I did last year with the previous cohort. So as a short refresher, I'm going to remind you about the main points of what we learned last 2 weeks. So first of all, we learned about the central limit theorem. So I gave you another video as well last week to introduce you to the concept. And the central limit theorem shows that whatever the underlying distribution is of the population, be it exponential, be it normal, be it uniform, and be it whatever shape it may be, the main point is that it does not matter if you are considering the sum of the independent random variables. So here, if you are considering the sum, trying to get the pen here, trying to get my pen. Okay, so it does not matter if you're trying to get the sum. So here, if we have the sum, we know that we will then be able to describe the sum as another random variable, which will follow this normal distribution. Knowing the mean and variance of the original population, we can then define the sum of the addition of multiple points as this normal distribution. And based on that, we can then convert it to a standard normal random variable as well. Similar to that, we take the concept of the mean that we already looked at previously, that the mean will make a normal shape regardless of the original distribution. And following that, we also know that if I were to take random samplings, and I average them, we also know that it will still follow a normal distribution following these two parameters. So we know that there are two things that I can conclude from the sample about the population, which is the sum and the average of the samplings. And if I were to change it into a standard normal random variable, then I would then be able to compute it as follows. Okay, so give me a second. Okay, so what we did in this first chapter, I'm going to try to simplify it a little. So we have, where's my pen? We have a sorry guys, have not been doing an on. Okay, so now that we have this theory, what we can conclude is that if I have an entire population here, a large one, which I obviously cannot study all of the time, I can just take a sample, and from this sample, I could compute that. And using the central limit theorem, I can then conclude two things. The first one is that the sum of these x's, so here I have x1, I have x2, and so on, the sum of the x's will be normal, as well as the average of the x's will also be normal. If I know that it is a normal distribution, then I should have two parameters here, which are the means and the standard deviations, which we already saw here. So the first one is the sum. So the sum will follow n mu and n variance. So the sum here would have the parameters of n mu and n variance. And this one here will have the parameters of mu, doesn't change, and divided by n. So here will be mu, and here will be the variance divided by n. Okay, this is the first part, which is the distribution of sampling statistics. What we concluded, what we were able to infer from our sample. From our sample, we infer the distribution of the statistics. So not yet the actual value of the statistics. Now, in the second theory, in the second chapter, sorry, we now would like to study something a little bit more specific. We're still having the initial population as such. We have our initial population, which is very large. And we acknowledge that we cannot study the entirety of the population. So we do the next best thing. We take a sample. Here is my sample. It's the same sample that I took previously. This is my sample. And from this sample, I can take some statistics. Perhaps I can take that. So now, using this sample mean, I want to infer something more substantial than just the distribution of statistics. It's not sufficient for me to just know that, oh, apparently the means follow normal distribution, the sums follow normal distribution. It's not enough for me. I want to actually know the values of the actual mean from my sample mean. So since this is statistics and I do not want to get ahead of myself, I am going to use an interval estimate, not a point estimate. So if it were a point estimate, I would actually say, oh, my mean is 3.6. The mean GPA of a Fasilkom student is 3.6. But that would involve so many assumptions. So I'm not even going to try. But what I will try is I want to try to estimate the interval in which left end and right end, I want to estimate the interval between which I could find my mu. If I know my sample mean, I want to limit the possible values for my population mean, which is my mu. And we learned last Monday that there are a couple of scenarios that we will be handling in this class. There is the CI, the confidence interval that we just learned in the previous video, for a normal mean when variance is known, and confidence interval for a normal mean when variance is unknown. So there's two cases. It's like this, if I know the variance of the population, or if I do not know the variance of the population. So there are the first two cases, which I color-coded in orange and in purple. Second is when I have two normal populations. Let's say here, I'm going to change the color. Say I have two populations. So I'm going to first do that, the first one. This is the first case. I have an X from here, and I have two cases. Either I know my standard deviation of the population, or I do not know the standard deviation. This is the first case. The second case is if I have two populations and I want to measure, from here I can estimate mu. So here from these two populations, I want to estimate the difference of the means. So what's the difference of the means of mu1 and mu2? And I can compute it by taking a sample from each, getting the first sample mean and getting the second sample mean. I could, and there are also two things that I have to consider. Either I know both standard deviations, or I do not know both standard deviations. In that case, I will take an estimate. And in that case, this illustrates these two cases, which I color-coded in yellow and green. Finally, there is also a sample, the computation if the sample was obtained from one Bernoulli population. This is usually the case if your population is rather small, but we are going to skip that for now. So you don't have to think about it for now. I presented it briefly in class, but I think I'm going to leave it out of the evaluation this semester. So using these color codes, we have yellow, orange, purple for one population. We have the sample, we have a cheat sheet on how to compute it. Note that if you know the variance, you use your Z table. If you do not know the variance, you use your T table. Same case here for the yellow color and the green color coded one. Same here. If you know the variance, then you use the Z table and you use the variance that you know. But if you do not know the variance, then you use the T table and you use an estimator of sigma. So here, SP2, basic SP square, it's basically you are trying to estimate the two variances, because although you don't know them, the difference of mean of two populations when variances are unknown, but you have to assume that they are equal. In many cases, if you are presented a question of two populations where the variances are not given, you may assume that they are equal. So these are the four things. Okay, having said that, all of these materials, now we are going to go on to the first exercise. I'm going to let you guys read it before I start. I'm going to let you guys read it before I start. And I'm going to solve these problems one by one. So let's look at what information we have here. So at the moment, what information that we have is, I'm going to label it one by one. What things do we know? Okay, we know that the height of pine trees is normally distributed with a mean of 3 meters and a standard deviation of 12 meters. Okay, so I'm going to declare that first. Please don't forget to do this declaration if you are solving a problem. So I'm going to first write that X is a random variable that denotes the height of pine tree. Okay, the height of pine tree. And I know that X is normal with a distribution of 3, normal distribution of 3 as mean, and a standard deviation of 0.12. Don't forget that when you are declaring the random variable, the parameter that you have to put here is not the standard deviation, but the variance. So don't forget your square over there. Okay, so in order to establish sustainable and responsible logging, the company is only allowed to cut down trees that are between 2.7 and 3.2 meters high. Okay, so first of all, the first problem here is compute the probability that a tree cannot be cut down. So if I know that it has to be between 2.7 and 3.2 right there, then I know that I would need to compute the upper and the lower probabilities in order to get the question. The question says cannot be cut down, right? So cannot would be there and there. Here I have two options. I could compute the probability of the X being larger than 3.2 plus the probability of X being less than 2.7. I could, or alternatively, I could opt to compute the middle part only. Remember that all sums of probabilities will be equal to 1. So I could compute it as 1 minus P being between 2.7 and 3.2. Apologies, these are the two alternatives that I could compute. I'm going to put a short pause here for you to try to absorb what I just explained. And if there are any questions, you can go ahead. Short pause. Okay, so this second question is going to be talking about the confidence intervals. So confidence intervals is what we already talked about on Monday, and also the initial video in the beginning of the class was talking about. So we can consider different levels of confidence when we are constructing our interval. So if you recall from our previous drawing I did over here, what we are trying to do now is, instead of just getting the distribution of statistics, I want to actually be able to estimate a certain interval in which I know my parameter will fall in. So the mean, for example, if I know the sample mean, I want to know the population mean. And this population mean, I accept that I will not be able to get an exact number, but I would like to get an interval within which I know my mean will fall. We already talked about it in class on Monday, that when I say that I'm using a 90% confidence interval, it does not mean that I'm 90% sure that I will get the correct mean. And it does not mean that there is a 90% chance that I would correctly obtain the mean. But it shows that 90% of the time, I will get the population mean. Since when I try to get the interval here, when I try to get the interval of my mean here, the interval of the values of my mean, I get it from taking a sample, right? Taking a sample and then getting a a sample mean. But I could do it many times. I could do it again here. I get another sample, I could get another one, and so on. And from each of these samples, I could get another interval. And 90% of the time, the interval that I get will indeed correctly have the sample mean. So, the population mean. And that was what was talked about in the video that I showed in the beginning of the class as well. If I raise my confidence level, like for example, I use a 90% confidence interval versus a 99% confidence interval. So if I say 99%, that means more times than not, I will estimate the interval correctly. The mean will actually fall in the interval. But if I say 90%, that means I have a bigger possibility of being wrong, right? There's 10% chance no, that's wrong wording. 10% of the time, I will not get the correct mean. So there's two things that happen. When I get more confident, that means I want to ensure that 99% of the time, I do indeed include the mean in my interval. The way I do that is by widening my interval. So if I use a larger confidence interval, a larger level of confidence, that means my interval will also be larger. You may think that makes it not precise. Yes, it does. But it does give you a larger chance to accurately create an interval so that your mean is included. Imagine if you made a very, very small, a narrow interval, you have a big chance of not including the actual mean because it's narrow. That way we make it larger. That way there's a bigger chance that you actually do include your interval, your population mean in your interval. So you can see here that it's kind of like tricking the system, so to speak, because what you're trying to do is trying to ensure that 90% of the time you are correctly creating an interval that includes the population. Okay, so I'm going to see what information we know here. We know here that we have sample size. Okay, we have our n. We have a sample mean, which is our sample mean. The next sentence says, assume that the population standard deviation is 4.8. This is the population. So if we go back to our initial drawing of population and sample, this is how these map out. This is my population. This is my sample. From here, there are 140 data points in my sample. And there, from these 140 data points, I get a mean of 18.4. Assume that the population standard deviation is 4.8. It's this one here, 4.8. So in this case, we know that we're dealing with a normal distribution, and I know the population standard deviation. So the case that I am currently handling is CI for a normal mean when the variance is known. Obviously, you are given the variance just now, or you're at least given an assumption that the variance is known, which is 4.8. Okay, so we know that the case that we're handling is that first case. Okay, so first, what we want to do is I want to compute the 90% and the 95% confidence interval. I'm not going to compute this until the end, but we're going to try to compute both. So this is the 90% one. This is the 95%. What will be different? When I'm talking about a 90% confidence interval, that means my alpha is 0.1. When I'm talking about a 95% confidence interval, my alpha is 0.05. See the difference here? We are using a different level of confidence and different alpha for both. Okay, so using the equation from the previous slide, I'm just going to copy it here so that we can reference it. We already know that it is the first case. Copy that here, put it in the corner. Hopefully you can still see it. Here, I'll put it in the corner there. And I'm also going to assume that we're talking about a two-sided CI. So I could use a one-sided CI, which is one-sided CI, which is not limiting one end. See, it's an infinity here, but I'm only limiting one end. But in this case, I'm just going to construct a two-sided one. So I'm going to keep that there on the top. Do that so we know what we're talking about. Okay. So what I want to do now, where's my slideshow? There it is. What I want to do is for the 90% one, I'm going to use that equation using the alpha that I have. So I'll just plug in the values. My mean should be in an interval of x bar 18.4, right? Minus, I'll skip that part, z alpha, I'll skip that for now. And here is my standard deviation, 4.8, divided by square root of n. And the other hand is 18.4 plus, I'll skip the z, 4.8 divided by square root of 140. So I'm going to look up now our z alphas. So our alpha here at the moment is 0.1. 0.1. Oops. This is our alpha, 0.1. But see this equation. What I need here is not z alpha, but z alpha divided by 2. So in this case, I will need to obtain z alpha of 0.05. Remember, when we were talking about the z alpha notation, we looked it up over here, and then we looked up the values up in here. So if I wanted to get z alpha of 0.05, then I would need to find up to 0.95. Where is it? 0.95. Remember when we did this in class? It was somewhere up here, 0.5. It's somewhere up here. So I would estimate that it would equal to 1.65 something, right? But don't worry, it is, since these alphas are often used, we already have the information right here. See in the z table that I gave you on scaling, you have this here. So in this case, since I'm using a z alpha of 0.05, then I can immediately use this value here. when I have an alpha of 0.05, then my Z alpha is 1.645, which is consistent actually with when we were trying to find a 0.5, a 0.5 here. It's somewhere a little bit lesser than 1.65, which is indeed correct. It's 1.645. So now I'm going to use that value here since I need to get Z of 0.05, which was, we already looked it up, it's 1.645. 1.645. And I'm going to let you finish the computation here. Similarly, if I use a 95% random confidence interval, then my mu would fall in the category of, in the range of, sorry, not category, 18.4 plus minus, note that it's the same, yeah, plus minus of Z, I need to divide it by 2, alpha, oh, sorry, I need to compute Z 0.025. Do we have that information? Yes, we do. With an alpha of 0.025, it is 1.960. So here, the value I need to use, this Z 0.053 is 1.960. So in this case, that would be 1.960 times 4.8 divided by 140. So this is the computation of a 90% and a 95% confidence interval. And for the second question, are they the same? Obviously not. They will be different. So basically, it goes back to the explanation that I gave in the very beginning. Since I use different level of confidence, that means that I'm declaring that 90% of the time I will be correct, or 95% of the time I will be correct. If I claim more, like in the case of 95%, that means I have to be sure of this. I have to be sure that 95% of the time, 95% of the time, my interval that I constructed here, this interval will indeed contain the actual real population mean. And as such, usually this interval here will be wider because I want to give myself leeway. I want to give myself a good margin so that I can confidently say that I will be correct 95% of the time. And if I only need to promise 90% of the time, then likely this would be a little bit narrower. Narrow. How do you spell narrow? Narrower. Okay. So I'm going to stop here because I'm already over by 3 minutes. Apologies. Any questions?